So in our previous lesson, we discussed sort of the idea of what a power series is, this idea that it's kind of like an infinite polynomial, and then after that we discussed the idea of the interval of convergence, saying that we could find out what values of x this series would converge for. But I think an interesting question is, what does that series actually converge to? And in today's lesson, I'm going to be talking about one specific type of example, and that's where a power series actually approximates a rational function, right? And I'm actually just going to sort of jump right into an example. Let's look at a power series, right? Let's say that we have the power series 3 plus 6x plus 12x squared plus 24x cubed, and so on. And so first of all, is this a power series? It certainly is. It looks like a polynomial. It's got a plus dot 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 on the end, so it's an infinite series. The question is, do we recognize it as anything else? And I, for one, because I wrote the problem, I recognize that this is a geometric series. Now, what do I mean by that? I mean, like, look as you go from term to term. Getting from here to here means multiplying by 2x. Getting from here to here means multiplying by 2x. Getting from here to here means multiplying by 2x. Right? This seems pretty clearly to be geometric with a first term of 3 and a common ratio of 2x. Now, here's where this really gets exciting. We learned earlier in this chapter, actually right at the beginning of chapter 8, that if you have an infinite geometric series, the infinite sum will be equal to the first term over 1 minus the common ratio. Right? So what that tells me is it tells me that this power series that I wrote down, because it's geometric, if I added it up forever, the infinite sum should be the first term over 1 minus r. So it should be 3 over 1 minus 2x. And this is really exciting because it means, wow, like this infinite polynomial-ish thing is apparently the same as this. But there is a catch. This is not like universally equal to this. They are only equal to one another on the interval of convergence, right? So something that I need to figure out is, for what values does this actually work, right? And so think about what we did in the last lesson. In the last lesson, in order to figure out what the interval of convergence was, we applied some sort of test, right? Well, because this is geometric, I'll just apply the geometric test. How do we know whether or not a geometric series converges? Well, we know that a geometric series converges when the absolute value of the common ratio is less than 1. So in our case here, that means when the absolute value of 2x is less than 1. Right? And then we can apply the same stuff that we did in yesterday's lesson, right? That means 2x has to be sandwiched in between -1 and +1, right? Which means my interval of convergence is going to be between -1/2 and +1/2, right? I don't believe that we actually need to test the endpoints of this. And the reason that I don't think that we need to do that is that the geometric series is in fact not inconclusive when the common ratio is 1. The only exception is when it turns out to be 0, but I don't think that's going to happen. So I'm going to go with this being the interval of convergence, right? Now, in the context of the problem, what does that mean? That means that this power series is exactly the same as this function, that rational function, so long as you plug in something that's between -1/2 and +1/2. And I'd kind of like to show you guys a graph of that to illustrate the point. So what I'm going to do here is I'm going to graph, and I'm going to see if I can even pull off colors here. We'll graph in black the power series, which was 3 plus 6x plus 12x squared plus 24x cubed, and so on. And then in some other color, I'm hoping I can do blue in my graphing program, I will graph the other side of this, which we said was going to be 3 over 1 minus 2x. And so I'll bring that up for you. Give me just a minute. Okay, here they are. So I graphed in black this power series thing. I only went up to the third degree term, and so that's why it's not perfect. Like if you look at the graph here, right here is where negative a half is, and right here is where positive a half is, and you can see centered around 0. My black polynomial is doing an awesome job approximating this this rational function. And if you're interested, I'd recommend, get out a graphing calculator, put on the 4th degree term, the 5th degree term, the 6th, 7th, 8th degree terms. The more terms you add on, the better this is going to get, to the point that it's awesome and perfect between negative 1/2 and positive 1/2, and a complete failure everywhere else. But on that interval of convergence, it does an awesome job. In some sense, that's all I need to say in the first video. I have actually 3 other examples prepared. I don't know that I'll go through all 3 of them, but I'll go through probably at least 2 of them. So if you should definitely stick around for at least 1, if not 2 more of these. So let's take a look at another example. Let's go back to black here. So suppose I gave you this series. What if I had 5 minus 15x plus 2 plus 45 x plus 2 squared minus 135 x plus 2 cubed, and so on. Sorry about the cubed there. So how would I write this thing as, how would I take this power series and find out what function it represents? In this lesson, the only things we're focusing on are these rational functions, so the hope is that you'll be able to see a first term and a common ratio. Right? Well, it's pretty obvious here that the first term is 5. Yay. As far as the common ratio is concerned, you'll notice this is alternating, which means the common ratio is going to be negative. Right? So this is going to be negative, and what is it being multiplied each time? Looks like it's negative 3x plus 2. Right? So wonderful. Now that I have those things, I can say that this infinite series, the sum on n equals 0 to infinity of 5 times negative 3x plus 2 to the nth, because that's effectively what it is, that thing will be the first term over 1 minus, now my common ratio is actually negative, so this will be plus 3x plus 2. And you can either leave it in that form, or you can simplify, like you could, make this 1 plus 3x plus 6. Heck, we could even make this into 5 over 3x plus 7. And I mean, any of these are correct. So there it is, yay. What about the interval of convergence? The interval of convergence. Well, for the interval of convergence, I'm supposed to take the absolute value of the common ratio and make it less than 1. My common ratio is negative 3x plus 2. Right? So, let's see here. The absolute value will take care of the negative there. I'm going to have negative 1 is less than 3x plus 2 less than 1. I'll divide all the sides by 3. Negative 1/3 less than x plus 2 is less than 1/3. And then when I subtract 2, I'll get negative 7/3 is less than x is less than negative 5/3. And this is my interval of convergence. Note that this thing is centered. Note, we are centered at x equals negative 2. And how do we know that? We saw an x plus 2. X plus 2 means we've got to be centered at negative 2, right? I could do the graphing thing and show you this one as well, but I want to save time. I want to get to one more example without dragging this lesson on for too long. So one last example, and I hope you guys will try this one on your own. So this one, I'm going to give you the power series, 25 minus 5x plus 3 plus x plus 3 squared minus x plus 3 cubed over 5 plus dot dot dot. And I'd like you to find out what this is equal to. What rational function is this equal to? So first you'll want to find the first term. You'll want to find the common ratio. Once you have that, you can plug it into the formula and then find the interval of convergence. So hopefully you're pausing and trying that on your own. So the first term is clear. It's 25. Now for the common ratio, it looks like we're dividing by 5 each time. But we can't divide for a common ratio. We have to multiply. So that means you're going to be multiplying by 1/5 each time. And it's alternating, so it's negative 1/5. And then, of course, we've got an x plus 3 that's being added each time. Right? So this thing is the same as 25 over 1 minus. Now, this thing is naturally negative, so you're going to be subtracting a negative that's plus 1/5 x plus 3. And that's a compound fraction. I'm never happy with that. So when we see something like that, what you'll want to do is multiply top and bottom by 5. 5, because if I do that, it'll cancel with that thing that's there, right? So when I multiply that in, I'll end up with 125. 125. This pen is not cooperating today. 125 over 5 plus x plus 3. And so I could simplify that further to get 125 over x plus 8. And that is apparently the same as that power series on the interval of convergence. So the last thing we have to do is work out that interval of convergence. Right? So the interval of convergence. And again, if you didn't do that on your own, try it on your own. We're supposed to say the absolute value of the common ratio has to be less than 1. So again, that negative is going to go away. I'll get negative 1 is less than 1/5 x plus 3 is less than 1. Multiply the 5 over, get negative 5 is less than x plus 3 is less than 5. And when you subtract 3, negative 8 is less than x is less than 2. This is the interval of convergence, and we had the series up above. But parting comment, if you're still watching and if you're interested, if you graph the original power series, a bunch of terms of it, say up to the 5th degree maybe, and then you graph the rational function, because this has such a long interval of convergence, it's really cool because you can see how much more of you can really see how well it's approximating, and it's a neat thing to see. So if you're interested, check that out. There are 1 or 2 more videos coming tonight, so I hope you're able to make it through those, and I hope these are going well for you guys. So I'll see you in the next video.